Okay, welcome to Linear Algebra through Geometry NPTEL course. This is week 11. Okay, this is okay. This is week 11 of Linear Algebra through Geometry. Uh, my name is Bhavya, and I'm a PMR scholar from IIT Madras. Okay, okay, good. Okay, thank you for bearing with me. So, last week we saw a few concepts. Okay, and okay, before last week, what did we do? We did the four fundamental subspecies. Okay, this was week 9, and if you can recall, the four fundamental subspecies were the row space, column space, the null space, and the left null space. Okay, great. And we did a lot of problems in it, the concepts behind it, and their applications. And then week 10, which was the previous week. And by the way, the recording to week 10 has not been published yet. It requires some editing. There are two separate clips and it needs to be stitched together. So I'll try to upload that by tonight. Okay. And what was week 10's content? We had least squares method. So it was a deep dive into least squares method. Okay. Now today's week, which is the second last week, and by the way, this semester's problem solving session will not have any extra sessions that like we used to. Okay. So week 12, which is next week's Tuesday, will be the last problem solving session that we'll be having. Okay. Week 11 this time. Okay, we'll be focusing on diagonalization of matrices. We'll see an application also, but in general, we look at what diagonalization is and the concept behind it. Okay, so the question, okay, that we want to ask, okay, in diagonalization is the as follows. Okay, the question we want to ask in as in diagonalization is as follows. It is that given a matrix A, okay, can we write A as follows? Okay, and here the form is that A equals P D P inverse. Okay, A equals P D P inverse, and such that P is an n cross n matrix. Okay, and clearly it should be invertible. Okay, because I need a P inverse also. Invertible n cross n matrix. And what is D? D is a diagonal matrix. So the question itself is simple. Okay, what is diagonal? It is a matrix with just the diagonals filled and the off diagonal elements are all zeros. Okay, so can we write it in this form? So this is the question that we ask. Well, why do we ask that? We'll see that later on. I mean, there's a huge application coming in next week's content also, which mainly focuses on spectral analysis, how you can take advantage of the spectral form by looking at the diagonal matrix and so on. That will come on. but we'll come to the application later on. But this is the fundamental question that we are interested in. Can we write it as follows? Okay, and so it turns out that yes, we can, and we'll soon see when. Okay, in several cases, in particular cases rather. Yeah, go ahead.
So why are we interested in such a decomposition only, and why not in some other form of the decomposition of matrix? Like why are we not interested in a decomposition like say S and then T and then S transpose and then T inverse? I mean some other kind of the decomposition and how.
Yeah, we'll actually see that this kind of decomposition has some very nice properties. Okay. For example, we'll soon see like what happens if you multiply two matrices like PDP inverse and QD prime P inverse. Sorry, P. Okay, Q inverse. What happens if you do this? Or what happens if you do P D Q inverse Q D prime Q inverse? And I mean, you multiply two such matrices. What happens? For example, uh, we'll see in the spectral analysis form that actually uh, the nice thing about diagonal matrices is that it's very simple to calculate with. Okay, it's very simple to compute with, and that simplicity makes certain kind of calculations pretty easier. I mean, for example, matrix multiplication, powering, and so on. Okay, in fact, maybe to motivate this context, let's do the application first. Okay.
All right.
Okay. So let's look at question. Oh, okay. Wait, this is last time's question. Sorry. Okay. Just one moment. Okay. This one will remove it. So here's the question. Okay. Here's the motivation. Prove that if a matrix A is diagonalizable. Okay, rather I'll just take a screenshot. Prove that if a matrix A is diagonalizable as PDP inverse, okay, and where D is an n cross n diagonal matrix, then A to the n is PD to the n P inverse. Okay, so just to talk to you, matrix multiplication, okay, in terms of computational difficulty, okay, okay. I mean, some of you may not have a computational background. Some may not have a background in basic computer science, but in algorithms, you have a notion of measuring how efficient techniques are, algorithms are. Okay, and that is measured by how many steps you required according to the size of the input. In this case, the size of the input can be roughly said to be the size of the matrix. Okay, so for example, if you are given and A n cross n and B n cross n, okay, these two matrices are given to you. So, how many steps are required to multiply matrices A and B? Okay, So yeah, Rohan is saying order n cube. So if you have to multiply, then what do? You go across all the entries here and all the entries here. There are n entries here, there are n entries here. For each column, for each element for each of the n elements in row, okay, multiply with n elements in column. Okay, so this is multiplied with n elements. This is also multiplied with the same n elements. Okay, and added up with the next element. This is multiplied with the first element, and this is multiplied with the next column. But there are n columns each, and how many are there? There are n rows. Okay, and each of the n rows have n elements. So you have n times n times n. Okay, so these many steps are roughly needed. So that's what we call in what is called order notation, that it roughly takes some n cube many steps. Okay, this much amount of time. And so this is how we do it. And do we know how to do better? Well, this can be improved to something like n to the 2.7. Okay, 2.78 or something like that. And that's the best that we know. Okay, and this is what is called Strassen's method. You can look into it later. But another question is, if you have if you need to do powering a to the n, okay, how do you do this powering? Okay, how difficult is it? Well, what you can do is powering is something that is slightly simpler, okay, than multiplication. You can always say that, oh, it's just a into n into a into n, and so a into a into a, and so on. Okay, how many times? N many times. And so actually, what it should, I mean, if you multiply this first, then this, then this, then this, then how many multiplications will you need? You'll need n minus 1 many multiplication. So if you do the previous technique, then it means that you need n minus 1 times order of n. N minus 1 times order n cube, right? Or order 2.7. Okay. This should be the complexity of this problem. So this is roughly what? This is roughly n to the 4. Okay. Can you do better? Well, yeah, order n to the 2.81, is it? Okay, it's not 2.7. Okay, so it's even worse that we know it's 2.81. Okay, thank you. Okay, so you need these many multiplication. Any idea if you can do better?
If it is diagonalizable, are you
No,
asking
no, no.
about that?
I'm not yet talking about diagonalization.
Oh, in general.
Yeah, in general. I mean, yeah. Right now, forget about
uh,
diagonalization.
LU LU decomposition.
LU decomposition. Okay. If you will perform LU decomposition, okay. You can maybe that will make it slightly simpler, because now you just have some lower triangular elements, upper triangular elements, but it's not still clear. I'll give you a simpler instance. If you want to compute, if you have a number n, which is a natural number, and you are given p, which is also a natural number, you need to compute n to the p. Yeah, Goel, what do you think?
I could not understand this n raised to the power p idea. However, I vaguely remember that in the page rank algorithm, there comes a situation wherein a raised to the power n becomes equals to n kind of a thing, and that page rank takes the help of, I mean, something happens in that algorithm, and this a raised to the power n becomes equals to simple a.
Oh, okay, that I'm not sure. That sounds something like Fermat's theorem. But yeah, I don't recall the. You mean it? Page rank is something from OS, right? Or
No, the PageRank is, I mean, used by Google in the initial.
Oh, okay, that kind of page rank. Okay, okay.
That PageRank, and there a raised to the power n becomes, I don't remember how, but then it becomes, I mean, we get the original thing back. That happens.
Oh, okay, okay. That should be an application of Fermat's theorem, because Fermat's theorem says that a raised to the power p
P minus 1
is congruent to a mod p, right?
Mod p, yeah. But then that is not related to the number theory as such, and that PageRank is related to the, I mean, concepts and the ideas taken from the theory of matrices only, and not to the theory of number
Oh,
theory.
okay, okay, okay. Yeah.
Yes. But
So,
then to multiply to get this value a raised to the power n, I cannot think of anything better than of the order of n raised to the power 4, because I'll have to use a for loop. Even if I go for the traditional that matrix multiplication, optimal matrix multiplication algorithm which we use using the dynamic programming to find the optimal number of the scalar multiplications. But there
oh yeah,
also complexity of the matrix multiplication came out to be of the order of n cube only.
it'll still come n cube, and
But
you
then
have
there was matrix chain. Yes, there used to be a matrix chain having n number of the matrices, and then I recall that we used to compute that optimal number of the scalar multiplications in an effort of the
that's
order of
right.
n cube. And here
Yeah,
we are
yeah.
getting the order of n star. So probably that could be an improvement.
Yes, but even in that case, I mean, in that case, the question that is like, if you have matrices A1, A2, A3, and so on to AK, and each of these have like dimension M1 cross N1, M2 cross N2, and so on, MK cross NK. What is the bracketing required? Right. That was the dynamic programming algorithm, right?
Yes. To get
Yes,
the
but
optimal number. But then
yes,
it
yes,
also
but
but then it also gives you the order of the multiplication, and probably it gives you, but may not give you the multiplication as such, the final result as such. May give you the optimal value of the bracketing, right?
yeah, yeah. But in this case, the issue is that we are powering the same matrix, so each of these is equal to n cross n. So it
Sir,
does not
can you
matter how you
repeat the
bracket it.
question? Uh, so can you repeat the question once? Like, what is we are trying to find out?
Ha, ha, ha. So what I'm simply saying is, see, you have a times a and n many times, right?
Okay.
And it looks like you need to do n minus 1 many multiplications, and each of the
Okay.
n minus 1 multiplications requires n cube many steps. So this is what we have from the trivial algorithm. If you use that Strassen's method, then you can improve this by
Yes, sir.
2.81, right? Question is,
Right.
can you improve this?
So that
So
order of n cube thing that
uh,
will always remain. So if somehow we can do
that's right.
something good with the n minus one, maybe
That's right.
some log of something. If we do divide and conquer or some kind of a step to
Yes.
change, is
Yes.
it
Yes.
okay? Am I going in the right direction?
You are going in the right direction. Yes. I mean,
Okay.
if you need to do some kind of divide and conquer. That's right. Okay.
Yeah. Yes, sir. Go on. Yeah.
So Goel was suggesting that using this dynamic programming, this bracketing algorithm, it's okay. I mean, if someone does not have algorithms background, but what you are just saying is like, if you have given matrices A1, A2, and so on with different dimensions, possibly different dimensions, then how do you minimize the number of multiplications required by actually choosing the dimensions carefully. Sorry, not choosing dimensions, choosing the bracketings carefully, because matrix multiplication is associative. Okay, but I'm saying that this idea will not work, because anyway the each of the matrices are the same here, and anyway all of them are n cross n. It does not matter in which order you multiply according to this particular algorithm. Okay, so here is the idea. Okay, just give me one moment. I need to switch off low power mode. Okay, great. So the idea is what is called repeated squaring. Have you heard of it before?
No, sir.
Oh, okay. So this the idea of repeated squaring is like if you want to compute, let's say, 2 to the 10. Okay, let's say you want to compute not 2 to the 10. Let's go something. Let's say 2 to the 16. Let's say you want to compute. Okay, then you can either, yes, Satinder, any question?
Yes, that I was saying ki any power has been explained by I think it is in the Vedic maths, like I think it is by Bhaskara Chari, it has been explained, like any, like suppose to I think same
Huh,
method you are discussing,
huh,
like suppose if I want 2 power 30,
huh,
so first of all I'll 30 I'll divide by 2, so anyhow I have to get 2 power 15,
huh.
then
That's
15
right.
is there, so we have to divide, so it comes, one is the remainder, means ki we want 2 power 7, and then we have to multiply, we have to do squaring and multiply by 2
That's
something,
right.
we keep on, so that was explained by Bhaskara charge,
Oh, okay,
that
nice.
method.
That's I did not know that this came from
uh,
Vedic math. Interesting.
uh,
In fact, I think the credit should be going to him instead of calling
yes,
it repeated
everything
squaring.
what I am saying ki
Hmm.
whatever the things are there, na,
Huh.
that is from the ancient mathematics only it has been taken, and
Hmm.
from there only the advanced maths has begun.
Hmm. Hmm.
Means what I think when I go through the things, na, with the higher maths, and then I go with the
Hmm.
lower fundamental, whether it is Aryabhat or maybe Bhaskaracharya,
Hmm.
or maybe it is Madhava
Hmm.
or
Hmm.
Pingla, what, so all these mathematicians have a very deep knowledge.
Hmm. Hmm. Hmm.
Yeah,
Definitely,
so
definitely. So we should
so
be. Uh,
very proud of them.
that's right.
Yeah,
We should be giving credit to them rather than
yeah,
calling
yes,
it repeated squaring. Maybe we should call it Bhaskara's repeated squaring. We only need to reach 2 power 8 and then we can use two of them to get 2. Yeah, exactly. Exactly. Yes. So, yeah, that is exactly the idea. So, you just need to do 2 to the 8 times 2 to the 8. Right? And, exactly. So, 2 to the 8 to the 8. So, this can be written as 2 to the 8 times. And this can itself be written as, so this is nothing but 2 to the 8 squared. And this can be written as 2 to the 4 squared. Okay, this guy times 2 to the 4 squared. So this is nothing but it is equal to 2 to the 4 squared, and then you go down the rabbit hole, and this is equal to 2 square squared squared. Is that right? Yeah. So notice how many times are you powering? You are powering log of 16 many times. Number of powerings equals log of 16. Okay, and you do this, and then you go. So this is 2. Okay, this is, and so the idea is you do 2 square, you'll get 4, and then you'll square that again, then you'll get 16, then you'll square that again, then you'll get 64, then you'll square that again, and so on. Okay, so that is the idea, and this is the same idea that we'll use in matrices. Okay. Oh, by the way, what if you get something like 2 to the um, something like 2 to the 7, not 17. Let's say 2 to the 20. This is not a power of 2.
So then we can represent this 20 as a sum of the powers of 20.
Mm, that's right. That's right. So you can write it as box function of that log. Yeah, but box function will uh, you do the box function, but that will give you the
Oh,
lower
sorry,
bound on the
sorry.
numbers. Yeah.
I meant the floor function we should be using.
Huh, yeah, yeah. That's right. I mean, to
Sorry,
measure the number of
ceiling.
right,
Sorry,
to measure
ceiling
the,
function we should be using, no?
yeah, you'll require the ceiling function, and but that is to measure the number of steps, right?
Right. Yeah.
And uh, but what will you do in about
Oh,
the,
okay.
yeah, that's something. So
Okay.
you
That's
you
nice. Yeah.
can, yeah, you can choose the closest function, which is near 20, less than 20. Sorry, closest power of 2, which is less than 20, which is 16, and do plus, not plus, times 2 to the 4. Okay, and you can keep doing this process. Okay, and now you have 2 to the 4 here, so you can do repeated squaring here, or you can directly multiply if you want, if it's small enough, and you'll do repeated squaring here. Okay, so the number of steps will be increased by a little bit, but it is, if this was log 16, you can upper bound this by at most 2 times log 16 steps. Because if it was more than log 16, it means that this power was more than 16, which is a contradiction. Okay, number of steps. Okay, at most 2 times log 16. This is the same concept you will apply here. Yeah?
Sir, that upper bound is very upper, na? Can we restrict a little bit? Like
you can of course
works, but
you can do that.
So suppose in general I want to know that to calculate 2 to the power p, what is the most number of steps I could be required of? Like p can be a power of 2, or p can be some odd numbers as well.
Exactly. So it can be odd numbers as well. If it is an odd number, then you will get a long sequence of decompositions, right, which you need to add together. So that will be a bit messy to calculate. So that's why log is anyway already a small, log n is already a small number, and if you just do 2 times, it's just a constant factor. So it looks like it is good enough already.
Okay.
If you want a tighter bound, you can calculate it, but will you get a closed form expression? I'm not sure.
Okay. So you're basically trying to figure it out from the order perspective. That
Yes,
it won't increase
that's right.
the order, right?
That's right.
Okay.
That's right.
Yeah.
Just a loose bound. Okay.
Right.
Sure.
Excuse me, what I was thinking, if you have to reach to 2 power 20, so it takes exactly 5 steps to reach 2 power 20. So I don't have the idea in terms of log, means that is, I think it is time factor, that computational time, I think log 16, whatever order you are writing.
Oh, okay.
That is the computational time. So if you take like what I'm thinking, it takes 5 steps by what the methods we have earlier.
That's right.
So 5 steps. So that is we start with we will start with 2 square. Then we will multiply by 2. That is the second step. Now we have got actually 2 power 5. Now we do the squaring. That is the third step. So now we have reached to 2 power 10, and now we have to square again. So in that final step, we will reach to 2 power 20. I don't know in computational time what it will take in terms of log. This
that is right, Satya. The log notation is not because of it's not because of a computational. It is a computational process, but it's not for this particular case. Log is just the opposite of exponentiation. Okay.
Okay, so I thought in computational time now we take how much time it has taken, so we write in terms of like I think order of log something we write.
That's right. Yeah, that's what we write, and that's something that I'm generalizing here also.
Okay.
So it's like, how do you represent it as a function? Because for 16 you had to do 4 times squaring it 4 times. Squaring it 4 times is nothing. So the number of steps is to get to 16 from 2 is log of 16, because so log of a base b equals c means that b to the c equals a. Okay, right? This is the meaning of log.
I have a little doubt here. Yes. So can't we reuse the calculation? Like say while
you
computing
can.
the value of
You can.
2 to the power 16, somehow we would be computing the value of 2 raised to the power 4.
You can, and that is how you can make it finer using that. So like Rohan was saying, this is a very loose bound. You can improve the bound by saying that 2 to the power 4 I already know. I'll just store it in my some space, in my memory, and then reuse this the computation, which is an idea from dynamic programming, right? And so any powers that will come later on will only be smaller, and we'll already know their values. So now the question is, okay, I already know this.
Excuse me. I think there is a little bit. If you are taking terms of log, so we have to write log of something. Like we will not write log 16. I think we'll write the value of 2 power 16 what we have calculated earlier. So that we'll have to put in that. No, if you are taking the log method, log 16 you wrote. I think that is wrong then.
No, why is it
log
wrong?
Log of some like 2 power 16 value will be something, suppose b. So log of b gives 2 power 16. No? Means b gives the b value is 2.
No, but
log 16
number of steps.
Yeah.
Okay, got it.
Okay. I get the confusion, Satinder. You mean that here the base is 2, right? And that's why you are saying that. But just look at this final value. Okay, 2 to the 2 to the 2 to the 2. You are squaring it 4 times. Okay, and what you have in hand is 2 power 16. Okay, so I'll just write it here. So what you are trying to say is, how can I reach 16, right, on powering 2? So how can I reach 16 on powering 2? So that means A is 16 here and B is the base here. And how can I reach to 16 by powering 2? So it becomes log of B, which is 2, and A is 16, equals that question mark, which is C. So that's what I'm finding. Log of 16 is 2. Is that clear, Satinder?
Actually, we are calculating 2 power 16, no?
That is what we are calculating. But yeah, I can see the confusion. That is what we are calculating. But that aside, okay, that thing, for example, let's say I make it 7 to the 16. The formula will still be the same because I'm squaring it. This 2 is coming from squaring it. Okay, even if I keep it 7 to the 16, the formula will still be log. So keep this what we are calculating aside for now. Okay, to the 16 is something we want to calculate. We want to see how many times do I need to power 2. Okay, how many times do I need to keep powering until I get 16? How many times did I need to power? 4 times. Okay, so I need to get to 16, and 2 to the, how many times do I need to square it? That is given by this C. And so so this is the form that I have. Then I do log A base B equals C, and then I get log 16 equals C. Okay, I get the confusion. Just stare at it. Okay. Okay, so okay, sorry. Goel was saying that you can reuse the computation. Yes, you can reuse the computation if you have enough memory to do so. Okay. So you can get even a better bound, but you can, for now, just let's take it as order log n. Okay. So it means that this can be improved further. So in matrix setting also, you can do repeated squaring. That's the point. You can do repeated squaring. Just observe that I'll just, if I need to do A to the 16, okay, I can write it as A to the, what is it, 8, not 8, 4, oh no, it is 8, okay, times A to the 8. And so this is nothing but A squared, 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 squared. So how many times do I need to do it? Log 16 many times. So if I have A to the n, I need how many steps? I need to power it order log n many times, times how much ever every squaring will take, okay, which is order n cube. Okay, so we've improved the bound. That's clear, right?
Yes, sir. Yeah.
Yes. Okay. Now, okay, we've spent a lot on that. Okay, although this is slightly out of scope of the course. Okay, so now the question is, okay, I want to do even better. Okay, I want to do even better in some sense. Is it possible to do that? Notice that squaring numbers is always simpler than squaring matrices. Matrices requires much more complexity, right? It's a very complex operation. Squaring numbers, well, it requires multiplying two numbers, but it's still fine, especially if it's a power of two. Okay, it's much more simpler. Okay, it's in binary, it's just shifting to the left, to the right. Now, here is an application, okay, and that was what Rohan was talking about, of diagonalization. If your matrix is diagonalizable, then powering becomes easy. Because if a matrix A is diagonalizable as P dP inverse, where D is a diagonal matrix, then A to the n can be written as P D to the n P inverse. Now, you might say something like, oh, but we are still squaring a matrix. Why is this simpler? Why is computing P D to the n P inverse simpler?
Because for diagonal matrices, we'll only play with the diagonal entries. So each entry squaring will only take one operation.
Exactly. Yeah. So if D is D1, D2, D3, and so on till Dn, and these are all zeros, D to the n is just D1 to the n, 0, 0, 0, D2 to the n, 0, and so on, and Dn to the n. Or D to the, sorry, let me write it as M. You'll get confused. So you just need to square the diagonal elements. Okay, so you can test it out later, but this is why it's simpler. Okay, I agree that you need to of course it takes time to calculate what is P and P inverse. Okay, it takes time to calculate P and P inverse. But let's say you already know the what is the decomposition. Okay, you already know what is P. Okay, then, and you already know what is P inverse. Okay, then the powering, okay, becomes a much simpler operation.
Okay. Why do we compute the power of the matrices? Where is the need to compute the power of the matrices?
Oh, see, there are several uses. Okay. For example, do you remember the random walks in matrices?
Yes.
Right. There we had some kind of matrix powering, right?
Yes, and random walk to the matrices is similar to the page rank I was talking about. Yeah.
Random walks in?
Random walk to the matrices is same as the page rank stuff which I was talking.
Yeah. So I mean, like some kind of Google search indexing algorithms will also use random walks. That's right. And random walks on graphs, reachability testing on graphs. Okay, right. You can do it using matrix powering, right?
Something similar to computing the transitive closure kind of thing.
Yes. You can even compute transitive closure and stuff using matrix powering. That's like it's very useful in graph algorithms. Okay, I do not know what other uses it may have in, let's say, some ML or AI, but at least in theory, yeah.
One thing I can think of. So basically, when we have a photo in our mobile and we rotate it, there are four options are given. One is 90 degree, then another 180 degree, then 270. So suppose I have a rotation matrix which does rotation of 90 degrees. I don't need to have other rotation matrices. If I can have the a square, a cube, and a to the power 4, all the rotations are in my hand. So maybe in that case also we can use that.
That is true. That is true, Rohan. Yeah. This is an application that you can derive from the lecture notes also. That yes, you can actually write a rotation matrix as different powers of D, and at its heart, it's a group theory application, but you can actually interpret it linear algebraically also.
Okay.
That's nice. Yeah,
Okay.
good. Yeah. And yeah, I mean, the fact of the matter is powering is still a very important application. Okay. So you have that. Okay. Now you need to say that prove that the matrix A is diagonalizable as PDP inverse. When D is a diagonal matrix, then A to the n is PD to the n P inverse. Okay. And the proof is like very straightforward. Okay. Proof is very straightforward. So you say that suppose A is PDP inverse. Okay. And all of these are n cross n matrices, and D is a diagonal matrix. Okay. And then just see this. Just see the fact that if you do A square, okay, let's say you do A square, then what do you get? PDP inverse times PDP inverse. Right. But matrix multiplication is associative. It does not matter on which elements you multiply first, which matrices you multiply first. So let's multiply these two. You get what? Identity. So what you get is PD identity DP inverse. Okay. And identity is nothing. I mean, when you multiply it with matrices, you get the same thing. So PD square P inverse. Okay, great. So the theorem is proved for this instance. Let's say you have something more non-trivial, that is A to the 7. Then this can always be written as P D P inverse to the power 6 P D P inverse. P D P inverse. Right, because A can be written as P D P inverse. Now what you do is you do the same thing. Okay, one moment. Okay. Now what you do is you do the same thing. PD
Power 5.
PD
P power 5 into PD P inverse power 5 into PD P inverse, then PD P inverse. Means we'll keep on writing and then we'll collect, I think.
That too you can do.
Or maybe using the previous result, like we have seen that P A square.
Actually,
it comes out with P D power 6 P inverse.
Yeah, that's right. Yeah, I think you are right. I think it's better not to use that technique. It's better to actually simplify this. Yeah, that's right. So if you do, actually, I wanted to come up with an induction technique. Yeah, that's right. But what you can do is, if this is 16, then okay. Here's what we can do. Here's what you can do. Sorry, yeah, 6. Here's what you can do. So let me decompose it into 3 parts. PDP inverse. Okay. Yeah, you can directly use induction to do it. That's right. So notice that this is nothing but PDP inverse to the 16 times PDP inverse. 6 is times PDP inverse. Of course, like you were saying, Satinder, I can keep decomposing this. Okay, I can keep decomposing this into PDP inverse, PDP inverse, and so on, PDP inverse. Okay, n many times, 7 many times, and then I'll just get it is equal to d to the 7 because of this result. Now, if I want to prove it for a general case, and for that I need to use induction. So to do that, if I have, I've proved the base case. Okay, I proved the base case, and I'll assume, okay, that for k minus 1, Okay, a to the k minus 1 is equal to d to the k minus 1. Okay, p d p inverse. Okay, and then it's just a matter of applying. So that is my assumption for induction, and now I want to do an a to the k for some k is greater than 2. Okay, I'll just do a to the k is p d p inverse to the k minus 1 times p inverse. Okay, and by my hypothesis I have this is equal to d to the k minus 1, and we already saw in the base case that when I multiply these two I'll get d to the k. So we've proved the general the theorem for a general n. Is that clear? Okay, good. Okay, good. Satinder, is that fine?
Yes, but we have to write, I think, P inverse also. Dk P inverse.
Oh,
It's
yeah.
okay.
What am I saying?
It's okay.
PD.
We have understood
Yeah.
that.
Okay. Yeah, thanks. Um, Great. So, so this, so now that we've seen that this theorem is true, means that if I know what P is, P inverse is, okay, all I need to do is power the elements of the diagonal, okay, and which will require lesser amount of computation, okay, and so therefore this is the advantage of saying that a matrix is diagonalizable, okay. Now, okay, and I hope this is a good enough application to study why it should be diagonalizable. Very well.
So how much information is lost when I decompose a matrix? Because since A in fact is equal to, if it is diagonalizable, means it can be written as a product of P, D and then P inverse.
Mm-hmm.
Capital D is something which could be which is so very redundant kind of a thing, or maybe redundant in the sense that this is a diagonal matrix. And now the most of the information of the original matrix A is contained in the matrix P and its inverse. And since from the matrix P we can derive its inverse if it is invertible. So therefore the most of the information of the matrix A is now contained in the matrix P. So
Is
will that
obtained in the matrix
is
P.
contained in the matrix P. So will that mean that we are looking for, and by the way, what would be the dimension of the matrix P here? Since the dimension of the matrix D would be n cross n kind of a thing. So what is the dimension of the matrix P here? Will it be,
P is also, we are assuming it to be n cross n. That is
oh,
something that will require.
oh,
Because we need n times n, no? So we'll need an n cross something, and here something cross n, but P is inverse, and they are inverses of each other, okay? And means they need to be a square matrix, so you'll have n cross n.
so eventually, ultimately, if we are reducing A and whose dimension is n cross n into something whose dimension is again n cross n thing, then what kind of a transformation is it, and how the information of the original matrix which was contained, the information which was contained in the original matrix A is now being preserved in this transformed or the modified matrix capital P.
That is right. I mean, in terms of information, it is still carrying the same amount of information because they are talking about the same thing. It is equal. A is equal to PDP inverse. In terms of maybe storing these, it may require more amount of space because you're carrying three matrices instead of one.
I ask this question, like say, because if I consider A as a matrix of having say features, and from the ML viewpoint, and if I want to reduce the number of the features, say in some sense, and I want that most of the information of those features should be preserved, and that is how I went for the decomposition of the matrix of
Yes.
features. And then I came up with another matrix, say P, and which is simplified in some form or to carry out the further operations. The matrix P seems simple. But then how this information is going to be preserved? Preserved because this capital D is a diagonal matrix and may not be containing that much of the information. And moreover, what would be the information loss overall? I mean, is there any criteria to measure that information loss is when?
No, I
When
mean, in fact, there is no information loss, right? Because they are equal. Or do you mean like if I don't, yeah.
So information loss, I mean that if I so this entire thing minus capital D minus diagonal matrix. So if I only talk about the information contained in the original matrix A and the information contained in some transformed matrix P, capital P. So therefore some information is definitely lost. I mean because we are doing this
I kind of get what you mean. It means what you mean is something like, let's say, you are saying because P is not a diagonal matrix. Let's say I add some kind of errors into P, okay, and look at the result on doing P the inverse. Instead of that, I slightly add errors into D. What is the effect of adding errors into D compared to adding errors into P? Right? You are saying because D is a diagonal matrix, it should contribute lesser when D is disturbed. Is that what you mean? Something like that?
Not exactly. I only mean to say that some information is there in the matrix A, and now we found that this matrix is diagonalizable, and so I could write this capital A in the form say PDP inverse. And my point here is that this D matrix is something which is so very predetermined kind of the matrix. I know its structure. It's a diagonal matrix. So if I remove this D from here, from the information content viewpoint, if I remove D from here, and now I'm only so somehow I have transformed this A into a matrix P. And by the way, it so happened in this case that the dimension of P is also n cross n. So as such, there is no change in the dimension. So now clearly, if we are able to write this A in this form, if we are able to decompose A in this form, then most of the information of A should get preserved in the matrix P, and the matrix P should be simplified. I mean, should be a simpler form of the matrix A to carry out some operations, and that is how we are going for such a decomposition.
See, the issue is okay without D, P does not make much sense. We'll see soon, okay, why D is very important because there is a particular way to actually diagonalize a matrix A. Of course, it may not. Is it unique? Yeah, it should be. It is unique. There is a particular way to diagonalize a matrix. Okay, and we'll soon see why D is equally important. Okay, if you don't have D, okay, and you replace it with let's say all ones or diagonal having all ones, then you should be getting something that may not make sense. It may not be possible to approximate A, okay, without doing this. So I'm not totally sure whether I answered the question. Okay.
So if I ask a slightly related question, that if I compute the eigenvalues of a diagonal matrix, what would those values be? Or do we have some established results related to the eigenvalues and the diagonal matrices?
That's right. I mean, we'll look at how eigenvalues are related. I mean, to diagonalization soon.
Okay.
Yeah. Fine. Okay. Yeah, I think Rohan has written something in the chat. P and cross and is still there.
No, sir. It's fine now. So basically, I was trying to understand what Goel sir was saying, that why.
Yeah.
I was getting confused whether he is want to have a trade-off between A and D. So I was not getting that point. That's why I wrote that. Now it's clear. We can
Oh,
move on.
okay.
It's fine.
Oh, okay, okay, great. Okay, yeah. Let's. Okay, for now, let's move on then. Okay. Um. Okay, yeah. So we'll come to computing diagonalization of matrices. Okay. Just before that, we'll do an exercise that we already know. Okay. We'll do an exercise that we already know how to do, and that is computing eigenvalues and eigenvectors. Okay. Yeah. Okay. Great. So the question saying compute the eigenvalues and eigenvectors of the following matrices. Write their algebraic and geometric multiplicities. Okay, we'll come to what algebraic multiplicity, geometric multiplicities are, but let's just first compute the eigenvalues. Okay, I hope you all remember what eigenvalues and eigenvectors were. Okay. Um, I hope you remember what eigenvalues and eigenvectors were. So, oh, okay, that is very quick. Good. So it's just those values. For example, if I have a matrix A represents a transformation, right? I want to compute those vectors, okay, which are unchanged by performing transformations. So if I do AX equals lambda x, okay, um, then I want this scalar, okay. This is a scalar. Okay, so applying A on the vector x will only scale it, okay, and not change the value. Okay, so that is what is meant by this. And so what do you do to compute eigenvalues? You do determinant of A minus lambda I equals 0. So what you do is here determinant of 6 minus 1 2 3 minus lambda 0 0 lambda equals 0, determinant of this. So which is nothing but finding the determinant of 6 minus lambda minus 1 2 and 3 minus lambda, okay, equals 0. And so this becomes 6 minus lambda times 3 minus lambda, okay, and minus will become plus 0. So you have 3 is 18 minus 6 lambda minus 3 lambda plus lambda square plus 2 equals 0. So this will be lambda square minus 9 lambda plus 20 equals 0, right? And therefore you have lambda equals 81 p square minus p, sorry, minus p, which is 9, and 81 minus 4ac, which is 80, divided by 2a, okay, and therefore it is 9 minus 1 divided by 2 plus minus 9 minus 1 divided by 2, which is 4, or 9 plus 1 divided by 2, which is 5. So is that what you wrote? 5 4. So it means that there are two possible eigenvalues, okay, for this. Now, but so this is the amount by which those vectors will get scaled. And what vectors? The eigenvectors. Okay. Now, how do you find the eigenvectors? Well, you plug the equations back. Okay. Assume, suppose x equals x1 comma x2. Okay. So what you do now is, okay, ax equals lambda, okay, or you can actually do ax minus lambda a and a x minus lambda, no, yeah, you can do a of x minus lambda. Okay, so that's what you can do. Okay, great. Eigenvector for lambda is equals 5 is 1 0. Row sum is 5 1. So okay, yeah, good. Okay, but yeah, if you want to do it the traditional way and I want to substitute it, then I get ax, which is 6 minus 1 2 3, 6 minus 1 2 3 times x1 x2 equals, let's say lambda equals 4 first. Okay, then I get 4 times 6 minus 1 2 3. Oh, okay. What am I saying? This makes no sense. X. 4 times x1 x2, right? So now what I get is 6x1 minus x2 equals 4x1 and 2x1 minus 3x2 equals 4x2, right? So let's find this out. I can equivalently write this guy as 2x1 minus x2 equals 0, and this guy as 2x1 minus 7x2 equals 0. So, and I can subtract this to get 6x2 equals 0. So x2 equals 0. Is that the case? And what is this? What does imply? This implies that x1 is equal to 0. Okay, so this will imply both are 0. Okay. I made a mistake somewhere, is it? There's something wrong. This should not be 2x1. Yeah, Mr. Shubham. Hello.
Hello. In the second equation, it will be plus 3x2, not minus. 2, 3, no? Two equations you wrote.
Yes.
So it will be 2x1 plus 3x2, and then you'll solve.
Right? Okay. Thank you. And yeah, Mr. Shivkumar, do you have a question? Yeah. Hello.
Uh, 3x2, if you take it on the right hand side, 4x2 minus 3x2 will be x2. x2 will be equal to 2x1.
x2 will be equal to 2x1.
From the second equation.
Yeah, from the second equation, x2 will be equal to 2x1. That's right.
From the first equation, 6x1 minus 4x1 that is 2x1, will be equal to x2.
x2.
So same equations we get.
So we'll get same equations, is it?
Same equation. x2 equal to 2x1. So repeated.
So these
or
are
the vector is the same. Eigenvector.
So you'll so we'll be getting okay great. Thank you. We'll be getting x2 equals 2x1.
Yes.
And so we'll be getting here the vector is x1 and here it is 2x1.
2x1.
Right? Yeah, thank you. And
so
here
take out x1 outside, it is 1 and 2.
I can write as 1. Great. Thank you. And this is a family of vectors. Okay, a scalar multiple of every one, or 1 and 1, 2 is what is called the eigenvector also. Okay, because any scalar multiple will still multiplying will always give another scalar. So 1, 2 is your eigenvector. Any scalar multiplication will still give you an eigenvector. And one more, Rohan, you had a eigenvector for lambda equals 4 is 1, 2. Is that what we have? That's right. So we have 1, 2 here. Good. So, and let's find the eigenvector for x equals 5 for lambda equals 5. Right? Lambda equals 5. 6 minus 1, 2, 3. 6 minus 1, 2, 3. And then we have x1, x2 is equal to 5 times x1, 5x2. Okay. Now again we'll do the same thing. 6x1 minus x2 equals 5x1 and 2x1 minus 3x2 equals 5x2. So therefore we'll have this is x1 minus x2 equals 0, and this one means that this will be minus 8x2. 2x1 minus 8x2 is 0. Right? So I can subtract 2 times x1 and so on.
Excuse me, sir. Again, it will come wrong then. It will be plus 3x2. So 2x1 is equal to 2x2. That will come.
Oh,
because again,
again made the same mistake. Thank you. Okay, so this 5 will go that there and it will be minus 2x2. Yeah, thank you. Okay, and this is correct.
Correct. It is.
Right.
I think it will come 1, 1.
Let's see. Oh yeah, these are anyway linearly dependent, so this will be 1, 1. That's right. So therefore, take any one as your free variable, and then it is this. So 1, 1 is your eigenvector. Okay. Now, okay. This let me call this V2, and this let me call it V1. Okay, this is your eigenvector, right? So now we come to asking what is the algebraic and geometric multiplicities. Okay. So algebraic multiplicity simply means the multiplicity of the roots of the characteristic equation. Okay. So this you have here. No, this is called a characteristic equation, right? How many roots are there? The degree of the characteristic equation, okay, is 2. Of course, so you'll have 2 values, 4 and 5. And the multiplicities means how many times the roots are repeated, right? So this guy has algebraic multiplicity 1, and this 5 is also repeated only once. No, so algebraic multiplicity is 1. I hope that is clear. Now, what is geometric multiplicity? Okay, notice that eigenvector does not just represent a single vector. Okay, it represents a family of vectors, and as you can see, it is x1 times 1, 2. So this is a vector space. right? X1 times 1, 2 is a vector space because it contains 0 also, and it's a scalar multiple of a vector, which forms a vector space. This is a vector space. This is also a vector space. What is the dimension of the vector space? This forms a line. This forms a line. If you look at it as a matrix, it is a matrix of dimension 1 with a single column. This is also a matrix of dimension 1 with a single column. If you write the vector space as a matrix. Therefore, that is your geometric multiplicity of eigenvalue 4 is 1, and geometric multiplicity of eigenvalue 5 is 1. It is the dimension of the vector space spanned by the eigenvector. Yes. Mr. Shiv Kumar, do you have a question?
No,
Oh, okay.
no question.
Yeah. Now, that is the geometric multiplicity. So, what's the time? 4:24. Can we calculate the same for this one? Can you try it? I'll give you some time.
Yes, sir. Sure.
Yeah. Okay. Calculate the eigenvalues, eigenvectors, and algebraic and geometric multiplicity for this vector B.
Is it eigenvalues are lambda equal to 1 and lambda equal to 2 to repeated? Is it correct?
I think so, Satinder. Yeah, that's
One is 2 and second is 2 with the multiplicity 2 means. I think so.
yes.
Maybe
Yeah.
if I've not calculated wrong.
I think that is the answer. Rohan is also saying the same thing. Yeah. Please go ahead. And finding the eigenvectors also.
Lambda 2, 2, 1.
That's right. Yeah. For lambda equals 1, 0, 1, minus 1. Okay.
With lambda minus 1, your eigenvector will be 0, minus 1, 1, t. Something like this. For lambda equal to 1, we have got geometric multiplicity 1.
For lambda
0, minus 1. Lambda equal to 1.
Yeah.
Eigenvector will be 0, minus 1, 1, t.
0, minus 1.
1 t. T means x3.
You mean like this?
Any.
Oh, okay. T is in the third coordinate.
Mm-hmm.
Is that right?
Is it for
lambda equal to 1, it's only 0, 1, minus 1. Or in that way, it has to make 0, minus 1, 1. So x2 and x3 are of opposite signs. T should not be there.
T, it is a multiplicative, no? So that is x3 will be the free variable, no? So x3 times means x3 we can take any number, no? That's why we are
x3 is free in your case. That's what you mean?
Yes, sir. Yes, sir. Yes, sir.
Okay, x3 is free, so this is what you want.
Yes.
T can't be in one place. That's what I'm saying. If you are writing T, then it has to be in both places. Like this option cannot be true. Like let alone this matrix. For no matrix, can be true, right?
No. I'm saying T is any number, no? T is any number, scaling factor. Like T
but
means
then you have to determine x2
suppose
as well,
x3
no?
So x2 is in terms of that only, no? x3.
Right.
x2 is
so in x2 also we have to put minus t.
So same. That's why t we have taken common, no? That's why.
So you mean
if you're putting this value 1,
you mean okay? This is also t, right?
Right.
So okay. So what you mean is this.
So 0, 1, minus 1, or this one, right?
Okay.
And for lambda equal to 2, one is 0, 1, 0, and another is 1, 0, minus 1.
0, 1, 0, and another
And
is
1, 0, minus 1.
1, 0, minus 1. Okay. So basically, you are getting s plus t times, right?
Yes, sir.
Yeah, that's right.
Right. Yeah.
Okay, st will replace the name. Okay. Okay, great. So there are two eigenvectors. You can see that. There are two eigenvectors. And here what you have? Okay, you have another eigenvector. By the way. Okay. You have another eigenvector. Now, notice that this is also a vector space. And it is a vector space with basis vectors, these two. Right? So you can clearly see that these two are linearly independent. So linearly independent means what? That the vector space spanned by these two vectors, okay, which is just S represented by vectors of the form x times 0, 1, 0 plus t times 1, 0, minus 1, okay, have dimension 2 because the basis, there are two basis elements, right? So dimension is 2. So what does it mean? Geometric multiplicity of lambda equals 2 is also 2. Okay, and what is the what about this? This is also a vector space, right? And of where the basis is 0, minus 1, 1, and which basis, there's only one basis, so the dimension of the vector space spanned by this particular vector, okay, is 1. So the geometric multiplicity is 1 here. Okay, so as you can see, the geometric multiplicity, the arithmetic multiplicity is 2 here, and the arithmetic multiplicity is 1 here. Geometric multiplicity is 2, and geometric multiplicity is also, correspondingly, geometric multiplicity is 2 and geometric multiplicity is 1. Okay, so does that mean that they will always be equal? No, that is not the case. In fact, interestingly, when the two are not equal, okay, is when when the two are equal, okay, is when you can always diagonalize it. When the two are not equal, what about that case? Okay, so we'll see that in the next question. Okay, but this is the first observation we can always make. Okay, is that algebraic multiplicity is always at most geometric multiplicity. Okay, why? Because algebraic multiplicity, okay, cannot be more than the degree of the characteristic equation. No, if the characteristic equation is 3, it will have 3 roots. Some of the roots are repeated. The sum of the algebraic multiplicity is always equal to n. Okay, and furthermore, what do you have here? Is this correct? Okay, no, sorry. That's why it's wrong. Geometric multiplicity is almost at most algebraic multiplicity. Geometric multiplicity cannot be more than the algebraic multiplicity. Okay, because geometric multiplicity, okay, talks about the vector space spanned by the vectors, the eigenvectors. Okay, and algebraic multiplicity represents the number of times that your roots are getting repeated. Now, the total number of many times that this particular root will be repeated is at most the degree of the characteristic equation. Right. Now, secondly, now what if geometric multiplicity is equal to algebraic multiplicity? That is something that we'll see. And what if geometric multiplicity is at strictly less than algebraic multiplicity? Okay. For all eigenvalues, okay, for all lambda, and let's say there exists a lambda such that geometric multiplicity is less than algebraic multiplicity. Okay, that is something that we'll see. Okay.
Sir, I have one doubt.
Yeah.
So basically, this question, okay, first let me tell you the question. So suppose A is a 10 by 10 matrix and it has two eigenvalues only, 5 and 7.
Okay.
So, and 5 repeats, let's say 4 times, and 7 repeats 6 times.
Okay. Okay.
So algebraic multiplicity of 5 is 4 and algebraic multiplicity of 6 is 7.
7, right.
Is it okay, or like did I made a miscount? So sum should be 10, right? Okay.
The sum should be
10
10
as well.
Yeah.
Okay. So yeah, lambda equal to 5 has algebraic multiplicity 4 and lambda equal to 7 has algebraic multiplicity 6, right?
Yeah.
So just to contradict you, I am trying to think geometric multiplicity of lambda equal to 5 is 5 and geometric multiplicity of lambda equal to 7 is 1 less 5. So why can't this scenario is possible?
Can you say
one I made,
so let's say lambda
yeah, sure.
1 is equal to
lambda equal to 5. Lambda 1 equal to 5. It has a geometric multiplicity as 5.
Geometric multiplicity as
and
5.
Algebraic multiplicity as 4.
Algebraic multiplicity as 4. Okay.
Yeah, right. And lambda 2 is 7.
Lambda 2 is 7.
Which has geometric multiplicity 5.
Geometric multiplicity is 5. Okay.
And algebraic multiplicity is 6.
Algebraic multiplicity is 6. Okay, great.
Yeah. And A is a 10 by 10 matrix.
And what? A is?
And A 10 by 10 matrix. That
okay, okay. Your A is a 10 by 10 matrix. Okay.
Right. So in one, I made the AM greater than GM, which is the right case, which we know it happens. In the latter case, AM is 6 and GM is 5. It happens.
Okay,
AM is greater than GM.
That's what you're asking.
But in one, I made AM to be lesser than. So why can't what particular thing it contradicts? If I try to create this kind of a scenario, exactly where I will get the contradiction?
Okay. Yeah, that's a good question. So you want to say what is the contradiction? So if AM has if your arithmetic multiplicity is larger than the geometric multiplicity. Geometric multiplicity is just the vector space that is spanned by the eigenvectors. So
this one is it possible geometric mean will be greater than arithmetic mean? Is it possible?
you're saying again, yeah?
Right.
No, I'm asking GM will be greater than AM is
Yeah,
possible?
that is something that should
It's not
not, that is
possible.
not possible. GM greater
That's
than,
why we
Because I think
have the
geometric mean
This one mean is
corresponds to the
multiplicity.
dimension number of bases what we get corresponding to the eigenvectors.
that's right.
So since the arithmetic multiplicity is 4, so I think because we have got what the eigenvectors we are going to get in that dimension, I think number of it depends upon the number of dimension, and geometric multiplicity will be not possible, I think, because we are
But why?
looking into the basis. I think I don't have the clear idea. Still, let sir explain.
See, the
So
thing
when
is,
you are trying to see a minus 4i, let's say for lambda 1 we are considering, so the null space we are looking at, the basically geometric multiplicity is what? The number of linearly independent vectors in the null space of a, right? For this particular a minus lambda I. So for a minus 5i, the null space we have, it can have 5 independent vectors. So actually it can't have, but I'm not getting why exactly it can't have. So
right,
I'm not getting the exact point which I can contradict.
the solution should not be very complicated. That's what I think. So what you have is you have 4 many 5s, right? And what you are saying is, no, actually this is the bad case. No, this is the good case.
Right.
This is this way.
Yeah.
Okay. So this is the bad case. Yeah. Now you have 4 many 5s, and you are saying that the arithmetic.
This will depend upon like what Rohan has said ki lambda 1 and what we have got, that will depend ki what A matrix has been given, because at random we can't take this scenario because it almost that depends upon the A dimension of A, then only we can
For any matrix it is not possible, right? No matter whatever kind of A you have, for any matrix A it is not possible. I know that.
Yeah,
But,
no, we are trying to contradict the. I mean,
okay,
something
but
should come up that.
like,
Yeah.
That only I'm saying that unless we are not knowing a matrix of dimension that whether it is m cross n, because by that
dimension is given.
No,
dimension is given 10 cross 10.
Acha, 10 cross 10. Okay.
Yeah.
Right.
So 10 cross 10. So lambda. Okay. Let me.
So when we are looking at geometric multiplicity corresponding to lambda equal to 5, we are trying to find how many linearly independent vectors are present in the null space of a minus lambda I, right?
That's right. Yeah.
Right. So a minus 5i, independent of whatever a is, the dimension is given 10 by 10. So a minus 5i, I have to show that a minus 5i cannot have more than 4 linearly independent vectors in its null space.
Yeah, that's right.
Okay. Can I say something about its rank? Or nullity cannot be more than 4, so rank cannot be
more than n. Then, so what you are saying is you are looking at the null space of a minus lambda I. Now, in the null space where lambda is 5, the null space for lambda equals 5, you cannot have more than 4 many linearly independent vectors. That's what you mean.
Right, exactly.
And why should that be the case? but this is nothing but the nullity
Right.
of
So the rank
A minus lambda I, and so the rank of A minus lambda I will be at most 10. Furthermore,
not at most 10. Okay. Okay, there should be a bound, no? Because if nullity is
already 4. I mean,
less
nullity
than
is
4.
is already okay. So wait, it's a bit confusing. So what you are trying to say is that the nullity should be
Less than equal to 4.
less than equal to 4. That's right.
So,
So
rank should be greater than equal to 6.
rank should be greater than equal to 6.
Right. And if it fails, suppose rank becomes 5, then is the problem. So whatever instance I have created, I have taken the rank to be 5 in that case. And that's why the problem is there.
So you
okay.
You can't say that, right? So let's say nullity is 5, which means that the rank is 5.
Right.
So now you want to say that the rank is rank cannot be 5. There should be a contradiction here.
Right.
That is not enough. You need to use the fact that
maybe some determinant or something like that, which will involve characteristic equation.
Yeah. No, but the solution should be much simpler than this. Okay. I'll look into this. Okay, I think it takes some time.
Sure.
Okay.
In the next class, we can discuss this.
Sure. Okay. Yeah. Okay. But yeah, good question. For now, we'll assume this. Okay, fact that geometric multiplicity is at most arithmetic multiplicity, right? And so there are two cases: either all of them are equal, or there is at least one eigenvalue for which it is lesser than. Okay. Now let's look at this question. Okay. So the same set of matrices. The same set of matrices, but now we are asked to diagonalize it. Okay, the same set of matrices, and we are asked to diagonalize it. Okay. So here's the result that we have. Okay. So here's the theorem that was discussed in the lectures. Suppose A. Okay. Suppose A has eigenvalues lambda 1 to lambda n. Okay. And eigenvectors v1 to vn. Okay. So here is the way to diagonalize A. Okay. So what I'll do is I'll assume D equals lambda 1, lambda 2, and so on till lambda n. Okay. And I'll assume P to be the matrix whose columns are v1, v2, and so on till vn. Okay. So far this is what we have, and what I'm saying is then A should be equal to P D P inverse. Now A should be equal to PD P inverse. Okay, great. We have a way to get this, but the issue is this always guaranteed? Okay. This is the P. You can always get eigenvalues. You can always get your eigenvectors. Okay, and you can arrange them in this order. Okay. Now the issue is that is it always guaranteed that you will get P inverse? Is it always guaranteed that you will get P inverse? This is not always the case. Okay, because when does inverse exist? Okay. P inverse exists when determinant of P is not equal to 0. Right? Or in other words, we've also seen what determinant not equal to 0 means. We need P inverse, okay, or P actually. So P should be a full rank matrix, okay, or all columns, which is nothing but eigenvectors, okay, should be linearly independent. Okay, so as long as you can get the eigenvalues to be linearly independent, you are good to go. Because if you can guarantee that all the eigenvalues are linearly independent, then P inverse exists, and if P inverse exists, then you can find P inverse. Okay, so this is the theorem that we saw in the lectures. So all we need to do is apply it, okay, in this context. So let's look at the first case. Okay, the first case you have 4, 5. Algebraic multiplicity is 1 and geometric multiplicity is 1. So this is where algebraic and geometric multiplicity actually comes into the picture. Okay, so suppose you have that geometric multiplicity is less than algebraic multiplicity. Suppose this is the case. Okay, geometric multiplicity is less than algebraic multiplicity. This means that for a particular eigenvalue, okay, this means that if you take the total, okay, you sum across all the geometric multiplicities, you take the sum over all geometric multiplicities, take the sum over all algebraic multiplicities, you'll always get that the summation gm is less than summation am, right? Because at least one of them, for one of them, geometric multiplicity is less than algebraic multiplicity, right? But what is summation over am n, and what is this summation of geometric multiplication? This will therefore be less than n, and therefore when you arrange them in these columns, it's never possible to get enough linearly independent vectors here. You cannot get enough linearly independent vectors and to perform this to get an inverse of P. Okay, so that is what we have. Thankfully, in this case, in both the cases that we have, it's geometric multiplicity is equal to algebraic multiplicity. Okay, so let's do this. That's in the first case. Okay, lambda equals 4, lambda equals 5, and here you have 1, 2, and 1, 1. Eigenvectors are v1 equals 1, 2, and v2 equals 1, 1. Okay, and so what you need to do? What you need to do is the diagonal matrix is 4, 0, 0, 5. Okay, and P inverse P is equal to 1, 2.
Excuse me, sir. Like
Yes.
when we are diagonalizing, means diagonalization, when you are doing, so what the lambda values we have got, So we have to write from descending order, no?
No, this not required as far as I know. As long as you preserve the order of so as long as you maintain that this is lambda 1, this is lambda 2, and this is v1, this is v2, it should be fine.
Like I think in singular decomposition we have to maintain this, so no order, I think.
Oh yeah. So single value decomposition, yeah, there we need to maintain.
Okay, so I thought
Yes.
here also we have
Actually,
to.
there is no.
But
Actually, there may not be any particular need to maintain. Some people say that okay, if the singular value, the greatest singular value is in the first place, so in that order. But the definition itself doesn't require the greatest singular value or the greatest eigenvalue in the first place.
Okay.
that is true. I mean, in several cases in eigenvalue computation, it makes sense to order them. For example, second eigenvalue represents a different context. You always say that first eigenvalue always means the greatest, second always means the second greatest, and so on. It has its applications in some cases, but as long as you, in most cases, as long as you preserve the ordering, it does not make a difference. For example, in this case also, it should not make a difference whether we order it or not. Okay. Okay. So then we need to compute a p inverse also. Is this
-1, 2, 1, -1.
Oh, great. Okay. Thank you. -1, 2, 1, -1. Okay. So, okay, if you've computed the inverse, then all you need to do now is p dp inverse. So then 1, 1, 2, 1, d is 4, 0, 0, 5, and p inverse is -1, 1, 2, -1. Okay. And therefore, this is your diagonalization. Now, if you just need to verify that this is indeed equal to a, then we can multiply, let's say, the first two, and then see that this is 4, 5, what is that, 8, and 5. That's fine. I think so. Now we multiply it, -1, 2, 2 -1. Okay. And we get -4 plus 10, 6, 4 -5 -1, -8 plus 10 is 2, and 8 -5 is 3. So that's right. 6. Is that correct? 6 -1, 2, 3. 6 -1, 2, 3. That's right. That's what we got. Right? So this is a sanity check that this is indeed the diagonalization. Now, okay, we have 4 minutes. Let's quickly do it for the other matrix also. Okay. So in this case, if you see, okay, the algebraic and geometric multiplicities are matching. Okay, of course, algebraic multiplicity is 2, then geometric multiplicity is 2, and algebraic multiplicity is 1, then geometric multiplicity is 1. Okay, they are matching. But how do we actually achieve? Because in essence, okay, we are getting, we are supposed to get 2 families of eigenvectors, right? And but here, notice that the basis is 2. I mean, the dimension is 2, and you have 2 eigen vectors actually, and as you can see that they are linearly independent with each other. So therefore, we are actually good to go. Okay, because all you need to do is you need to make sure that the ordering is preserved, and since they are linearly independent, okay, you don't need to worry about not getting a diagonalization. Okay, so you have 2, 2, 1, and you have 0, 1, 0, 1, 0, -1. Okay, so you have lambda 1 equals 2, and here you have 0 1 0 1 0 minus 1. Okay, and here you have lambda 2 equals, okay, let's rather do lambda 2 equals 2 1 0 minus 1. Okay, so it's almost like for a particular eigenvalue you have a unique eigenvector. Okay, 1 0 minus 1 and 0 minus 1 1. Okay, now what do? You do p equals 0 1 0 1 0 minus 1 0 minus 1 1. Okay, and d is just there. Now you should preserve the order. Okay, now you need to compute p inverse. I think, is there a need to compute p inverse?
Right. So give me just 1 minute until I'm telling you the p inverse.
Yeah. No, I'm thinking, can you do it more differently? Is this orthogonal? It's not exactly orthonormal. Is it orthonormal? No, it's not orthonormal. The norm of each of the vectors is greater than 1.
Okay, can we think like this, that what linear combination generates, because numbers are pretty much like 1 minus 1, so we can figure out what linear combination gives 1 0 0 in the first column. So that surely needs, we don't need to do that rigorous computation like adjoint of p and then divided it by det of p. Instead we can think of what linear combination of these three columns generate 1 0 0. So I need one second column, and yeah, I think we can do that. Let's see. If we have one second column.
Okay, you mean a more intuitive way?
Right. One second column, one third column. That gives me 1 minus 1 0.
Yes.
And I subtract one first column from it.
Yeah, you can think of that in that sense also. Some how do you get to the identity?
Right. So first column will be 1 1 1. That gives so 1 1 1.
Sure. Okay.
Sum up all the linear combinations. Yeah. So that will give you 1 0 0, right?
That's
and
right.
Second I need 0. Second is very easy to find. So 0 1 0 is already present in the first column. So we can have 1 0 0 in the second column. And third is also pretty much easy to find.
Will be,
let's see.
0.
Let's add first and last. So 1 0 1.
Yeah. Okay, great.
Yeah.
And now what do? You do P inverse. So basically, if you multiply 0 minus 1 1 times t is 2 0 0 0 2 0 0 0 1, P inverse is 1 1 1 1 0 0 0 1. And okay, yeah, so this is your decomposition. If you multiply them, you should be getting back E. Okay, let's see that. Should be getting 0 here, 2 here, and 0 here. So 2 0 and minus 1 0 minus 2 1, okay, times 1 1 1 1 0 0, okay, and this will be 2.
Is it last one is P inverse last row is 0 0 1 or 1 0 1? Little bit doubt is there. For the
Last row of
P
P
inverse.
inverse. Last row.
Is it correct? Last row. Is it correct?
See, let's verify. P inverse will be equal to
last row is 101, right?
1.
Okay.
101 is fine, yeah.
Is it fine? Okay.
Yeah, 101 is fine.
Yeah, this will be 0 0, and this will be 1, right? This will be plus 1, this will be
So the last row of P inverse is nothing but the linear combination of third row minus the minus second row in P inverse. So third row minus second row in P inverse is indeed 0 0 1.
yeah, sorry, yeah, go on.
Yes, sir. So I was just confirming that. So yeah, so I was basically taking the either the row combination or the, so it helps to multiply.
I've got it here right. 0 0 1 it is that I've got it. That's right.
Oh, yeah, right. So it's fine. 101 should be. P inverse is calculated right.
That's right.
Yeah.
It looks fine to me. Okay, let's go on. So yeah, okay. So this is 2. This is 2. This is 0. This is 2 minus 1 is 1. 2. This is 2 minus 1 is 1. Minus 2 plus 1 is minus 1.
Sir, it should be, first row should be 2 0 0 only, no? First row
should be
2 0 0. 2 0 0.
2 0, yeah, that's right. Sorry. 0 0.
Second row is good. So 1 to 1 is right.
This is also 0. And this is 1, right?
Right.
2 0 0 1 to 1 minus 1 0. 2 0 0 1 to 1 minus 1
Yeah.
0. Okay, great. Okay. So this is indeed a diagonalization of the given matrix. Okay, and so that is a method to calculate the diagonalization. It's not always possible. Yeah.
Excuse me, like for the lambda equal to 2, the algebraic multiplicity is 2, geometric multiplicity is also 2.
Right.
So we have got the corresponding 2 eigenvectors.
That's right.
So any eigenvectors will switch, means will give the different arrangements. Permutations of both the eigenvectors are not going to affect this diagonalization, I think.
That's right. Permutations will not affect
No,
as long as you preserve the order.
That only I'm saying ki, here we have wrote 0 1 0 at the first column in the P. If I'm going to take 1 0 minus 1, then also it is not going to affect. No, I think so. If I'm going to switch the order of the...
Yeah, that's right. It should not.
Okay. Because it depends upon the choice of the student ki, which order he has kept. So P matrix will be different for different students.
That's right. Yeah. There is nothing special about how you order it.
Because because the multiplicity is repeating, so means ki that order is not necessary that it will be same for all the students, like all.
Exactly. You can choose an ordering and stay true to it. Okay. But as long as the vectors and eigenvalues have corresponding
Okay.
Excuse me, sir. Sir, I have one doubt.
Yeah.
So suppose I have three distinct eigenvalues, lambda 1, lambda 2, and lambda 3.
Right.
They are distinct. Okay. So the corresponding eigenvectors are linearly independent or whatever. So I have done this diagonalization. Now I want to understand two.
Hello.
Will be unique.
Can you repeat that? Sorry.
Yeah. Am I audible, sir?
Yeah. Okay. Yeah. Can you repeat the
basically, I'm trying to understand. Yeah. To what extent this diagonalization is unique? So if I fix the ordering of the eigenvalues,
right,
lambda 1, lambda 2, lambda 3.
Yeah.
Then can I then is it possible to say the diagonalization is unique?
Okay. You are saying that okay, lambda 1, lambda 2, lambda 3 are distinct.
Right. And I have kept in the I have kept them in this order. That lambda 1 first, lambda 2 in the 2 by 2 position, and lambda 3 in the 3 by 3 position. So now my question is this diagonalization unique?
Let's try to argue that. Okay, so what you are saying is, so if I do a PDP inverse, and basically you are saying this is unique, right? There is no other way to do it. Then
yeah. So for a unique D, is the diagonalization unique, or we can have different P?
Unique. Can you have a different P? That is a good
right.
I think. Excuse me. I think it will be same. No, P will be unique because in T we are maintaining the order. No. I'm saying
not because of order. So I got you. So for order part, I kept that ordering first. But eigenvectors are not unique, no? So eigenvectors can be different for the same eigenvalues.
That is true.
Because multiplicity is 1, no? You are taking lambda 1, lambda 2, lambda 3, no?
Suppose you have taken the eigenvalue 5. Sorry, eigenvector as 1, 0. So I am taking the eigenvector to be 2, 0. With the same eigenvalue, we have different eigenvectors, right? We have infinitely many eigenvectors for the same value because it's some constant multiplied by 1, 0, right?
That is right. I mean, you cannot, with this assumption, you cannot directly say that it's unique. I mean, at least this particular argument should not be enough. That's what I think. Why should it render the entire ray to be uniquely decomposed into this case?
Okay. So if it is not unique, then what additional constraint we can impose on it to make it unique?
That is right. So you need to think about the general case, right? When A equals PDP inverse, and you assume that this is a unique decomposition. So it means that no matter what PDP inverse you take, this should not be very trivial to prove. So, and this is a unique decomposition. And
because there was a question similar to this in the assignment, it was about LU decomposition, and from that question actually I've started thinking in this way. So all the decompositions that I'll be studying, I'll try to understand whether they are unique or not. Let's say A equal to CR, LU, or whatever, and if they are not unique, then I'll try to put constants on them. In LU, we have seen that if the diagonal entries in L are all 1, then the decomposition becomes unique.
That's right.
So here, the first constant that Satinder was mentioning, that he was permuting the eigenvalues. So the eigenvectors in the P was also permuting. So first we have taken care of that. We have said the ordering of the eigenvalues are fixed. Let's say lambda 1, lambda 2, lambda 3 in this order. Now I can argue that for same lambda 1, I have infinitely many eigenvectors, though algebraic multiplicity is 1. Because eigenvector is always C into something, so I can change the value of C. So now what is the bare minimum condition that I can put on P, and I can say that now it is unique?
That's right. Yeah. So I'm thinking. See, firstly,
excuse me.
It could be
if we can think.
Yeah, Satinder.
Like what I'm thinking, what Rohan has said, if I'm getting that what actually is saying, can we take the eigenvector correspondingly what we have got to the particular eigenvalues, we have got the eigenvectors. Definitely there will be infinite eigenvectors. So if I'm going to consider the basis of that, no, what I've got, so general basis, but basis
But we
means
have
if I'm
infinitely
going
many
to
bases.
no, only the simplest one ratio. What we call in, I think, directional ratio. We call in math we say that direction ratio. I don't know what it will be. Once we decide the direction ratio, then it is confirmed that all the vectors will go in that particular directions only. Maybe infinite. So if we take the simplest of that ratio, like what we have got, like in x1, x2, x3,
Okay.
whatever the column vectors are there. So
Okay,
we
right.
take the simplest ratio. So that will
Good
form
idea.
the p unique as what I think. So maybe I don't know this part.
No, it's a good idea. So you're basically saying to normalize it. Let's normalize
Yeah,
it and have unit
yes,
eigenvectors on there.
yeah. That's what I'm saying.
Okay, right. So, sir, this is a good idea actually. He's saying that let's have norm of each eigenvector as 1. So let's normalize them. And after normalization, that will be unique. So I think it will work.
No, I mean, but no. So okay, then I think I misunderstood your question. You Are you saying that for what kind of matrices is their diagonalization unique? That's what I thought you meant.
Oh, no. For any kind of matrices, diagonalization will not be unique.
So no, I mean,
But
of
second,
course,
yeah.
you can
Okay,
have
okay.
infinitely many values for the as long as you preserve the linear independence. I mean, as long as you can have
Okay.
multiples of the eigenvectors, you're still fine, and it cannot be unique in that regard. But I was thinking that what if you change the vectors in P and then think about uniqueness in that regard? So that is how I had
Okay.
interpreted your question.
Okay. Let me understand you better. So you're saying if I change vectors in P, by what? Like by what I will be changing vectors in P?
So I change the vectors in P by linearly independent columns.
Okay.
Okay. And then, okay, first of all, I say A has this particular diagonalization, that is P dP inverse, where P is unique. Okay.
Right.
Where the diagonalization is, let's say I have PD in P inverse where D is a diagonal and so on. And I give you another diagonalization, okay, where the columns of P are not scalar multiples of the original P that I had.
Right. But linear combination of them.
Yeah, not necessarily linear combinations also.
Okay. So, but how they will become eigenvector then? So they won't have.
Yeah, that's
So
what
in
I'm
D
saying.
you want eigenvalues, right?
No, yeah, I mean, I'm talking about another decomposition. D may not even be
Okay,
eigenvalue.
okay. I think I'm getting you now.
Yes.
Okay, so basically you have A equal to PDP inverse in one hand, and then you are trying to have another decomposition. Let's say
Yes.
A equal to Q, B, some S.
Exactly.
So now are you trying to see that whether D is equal to, if D is equal to B or something like that?
Exactly.
Can you write it, sir? I think I'll understand you better if you write it.
Sure. So what I mean is there exists PDP inverse and QDQ inverse, or can you say something like that does not exist a PDP inverse such that A equals PDP inverse and QDQ inverse, where it's P is not necessarily the eigenvectors and D is not necessarily the eigenvalues.
Okay.
Okay, this is true uniqueness, right?
Right. Yeah. So basically, you're asking that can we have eigenvalues in the diagonal elements without having eigenvectors in P?
That's right. So I think that this is not the case. I think that this should not be unique because that would mean that you can never write a matrix in this form, which is strange to say. I think you should be able to write a matrix in this, any matrix in this form.
Right.
Okay. So okay, but that was what I was understanding. But by uniqueness. But what was your question about uniqueness?
Oh, okay. So I was asking very simple one actually. So I was saying that uh, let's say so when we have LU decomposition, we used to say that if we fix the diagonal elements in L as all one, then LU decomposition is unique.
That's right. Yeah.
Yeah. So now, if someone says that Ron is whether diagonalization is unique for this matrix A, so first I will argue no. If you permute the eigenvalues in D, so that will still be a diagonalization.
That's right.
But,
that's right. That's right.
That don't have. So now that person constrains me by saying that okay, what if the order is fixed, and then I will be arguing that okay, for the same eigenvalue I have infinitely many eigenvectors. And now Satinder is saying that okay, Rohan, you have distinct eigenvalues. So let's say the eigenvectors can only be normalized. So in that case, the diagonalization will be unique. But what if the eigenvalues are not distinct? Let's say some eigenvalue lambda 1 appears twice, and I'm keeping them in the same order only. Eigenvectors also in the same order. But now in a plane, there could be many normalized vectors, right? In a plane. So the two vectors that I'll be replacing for lambda 1, they are normalized, as Satinder said. I'm keeping the normalized criteria intact, but in a plane we could have infinitely many eigenvectors which are normalized, and they will act as a v1 equal to lambda 1 v1 and a v2 equal to lambda 2 v2 while having the norm as 1. So what is the one condition that we can impose on this diagonalization so that it will be unique?
Okay, Rohan, actually this point only I was asking in the beginning, no? If there are lambda, I think what you are telling, that part only I've asked in the beginning. If the multiplicity is more than 1, so because there will be the different now normal vectors. So if I'm going to permute that part for, so definitely that will be not unique. This only I was asking before, this part only, what you have raised.
Okay. So let me understand you. So you are saying permute. That's why I'm not thinking we both are saying the same thing. I'm not talking about permuting.
No. Actually, I'm telling that only in the P1 no part. If I'm going to do the like rearrangement of that part, no. So I'm going to get the different part. I think so. Okay, you continue that part.
No. Let me understand you, Satinder. I think you're saying something right. So you're saying that same eigenvalue. Suppose A has two eigenvalues repeated, right? Let's say lambda 1 and lambda 1.
Yes.
And now you have two eigenvectors for them. Let's say v1 and v2 for the same eigenvalue, which are linearly independent. So now tell me, by permuting, what do you mean?
I mean, if we are keeping in suppose C1, first one you are keeping in C1, and second one you are keeping in C2.
What is C1 and C2?
C1 for the lambda 1, we have got lambda 1 we have got two bases like two eigenvectors we have got for the lambda 1 because multiplicity is 2.
Okay. Right, v1 and v2. Okay.
V1 and v2. So in the first column I'm keeping as v1. In the second I'm keeping as v2. Now I can interchange now. So v2 I can write in the first place and v1 in the second place. So that will be I'm going to get definitely different combinations.
So you're permuting them.
Yeah.
No, they're basically permutation. So I am saying something different. I am saying let's not have v1 and v2 at all. Let's have some v3 and v4. Something completely different. But we can normalize them still, and that will be u1 and u2. So I am saying that I got your point. You are just permuting them, and I am just taking the linear combination of them. Both in both cases, it will be satisfied. Are you getting my point?
Yeah.
Right. So permutation I can easily restrict. I'll have to say that okay, Satinder, the ordering is fixed. So then that has taken care of the permutation part. But how will you restrict me when I say that I'll take linear combinations?
Rohan, you are still not getting that part. No? Like
ordering of the eigenvector I have fixed. Okay.
No. You're not getting that part. No, actually, how you can fix that part? Like just see. I think you have not understood that what I've said. Lambda equal to 2. Hello.
Right. Yeah.
Lambda equal to 2. We have got like v1. We have got 0, 1, 0.
Yeah.
And
Can you,
V2 we
sir,
have
can you
got.
go a little bit up?
Satinder, can
Then,
you
it'll be easier to understand, Satinder.
do you want me to
He's
write it
referring
here
to
so
that
that
problem actually.
your point is
Sir, can you write this part? What
sure?
I'm saying.
That
I'm
problem is
saying.
already here, no? He's referring to that problem only, I think. 2 repeats twice. So we have that.
Okay, we can go to
a
that
little
problem
bit
also
up.
if you want.
Oh, okay, cool. Yeah.
I'm telling you, like we have P matrices as 0, 1, 0. Can you write, sir?
Right.
Yeah,
And
sure.
1, 0, minus 1.
0, 1, 0, 1, 0 minus. Oh, you mean column wise?
I'm telling column wise.
Okay.
0, 1, 0, 1, 0, minus 1, and 0, minus 1, 1. This is P. I can write this P as like this also. 1, 0, minus 1.
Can you write the D along with it, sir? So it will be easier to understand. Just the D.
Sure.
For this particular P, can you write the D?
Okay, D will be 2, 0, 0.
Yeah, just give me
0,
right.
2, 0.
Yeah.
D, along with that D I'm telling.
Yeah. Just a sec.
Yeah. Okay. D will be
2, 0, 0.
No, you mean
0,
okay.
2, 0.
0, 2, 0.
And 0, 0, 1.
Okay.
Corresponding to this, my P matrix will be this also. No? Again, I'm telling column wise. 1, 0, minus 1.
Okay.
0, 1, 0.
0, 1, 0.
0, minus 1, 1.
0, minus 1, 1. Okay. So you've permuted the first and the second columns.
So it doesn't going to affect because
It's called P star.
This only I was telling.
Yeah. This is not going to affect as long as the D also you permute. No.
No, the D where D if I'm going to permute, then it will be the same. No, the D is same for both.
Sorry.
You can
Yeah,
see that.
D does not need to be permuted. Yeah. Yeah, in fact,
but
it's not exactly permutation because you won't get a diagonal. It's just swapping the elements, not permutation.
Right. But I can restrict this. So all we have to do is we have to say that the same eigenvectors, they have to be in this ordering. So 0, 1, 0 and 1, 0 minus 1, which you have swapped just now. If I put a restriction on that 0, 1, 0 and 1, 0 minus 1, that is the eigenvectors corresponding to eigenvalue 2, they have a fixed order. So,
yeah, that's right.
Let's say, right. Even then, I can come up with a different P, which is the sum of these two, and that will act as a eigenvector, right? Sum of these two divided by 2.
So you want to do sum of this two, but where? You mean you want to replace one of them by the sum of them?
Right. Will it act as an eigenvector, or I have to divide them by 2? Okay, Ax equal to lambda.
Okay, that's a good point.
Ay equal to lambda 1y. So A of x plus y. No, the sum will suffice. So if I take the sum, that will be an eigenvector, right?
It will be
with eigenvalue 2.
Span the same space. That's right.
Right. So when we are talking about eigenspace, eigenspace corresponding to lambda equal to 2. These are the two linearly independent eigenvectors that generates the whole space with dimension 2.
That's right.
So even if I restrict Satinder by saying that if you have two vectors, I have to keep them in the same order. So earlier I was imposing order on the eigenvalues. Now I am imposing an extra order on the eigenvectors as well. But still, someone can come up with a different linear combination which generates a different eigenvector itself. So we are not swapping anymore. We are taking a linear combination.
That's right.
So
now
we need a general condition.
So this is there is nothing special about these particular eigenvectors. I mean, as long as they span the same space, you are always good. In other words.
Right. So is there any spatial eigenvectors among eigenvectors? Just like standard basis in basis. So is there any special standard eigenbasis or something like that, which is regarded as standard?
Well, see, you can always normalize it and call it, but you want it special in this particular sense, no, in terms of diagonalizability.
Right.
In terms of diagonalizability, right?
Right. Yeah.
In terms of diagonal, okay, I'm not aware of that. Probably there is, okay. In terms of just special, then you can just normalize them, and normalized eigenvectors are usually what you would consider the standard eigenvectors, right? Yeah, in the diagonalization context, I don't know about any standard eigenvectors for that, but we'll look into it. Okay, I'll look into it.
Okay.
You
So,
had
sir,
asked another question also. I just want to recall so that I'll think about it. Oh yeah, that was
yes,
on
sir,
the.
I will do one thing.
Yeah.
That am greater than equal to 10. So whatever question is unanswered from today's class, I'll try to make a similar LaTeX kind of a file which you make, and I will send it to you. In the next class, we can answer.
Oh yeah, sure. We can do
that. Rohan, excuse me.
Yeah. Sure.
I'm not getting that how you can restrict that part by permuting that. No, what I've you have said you can restrict that one. No? So
right.
How by order? This I'm not getting. Like
Hi Satinder.
Right.
Yeah, I'll.
Okay.
Sorry, yeah. I will need to leave right now.
Right.
I have some commitment, but I can leave and leave the meeting open. Is that fine? If I do that?
Yes, sir. That will be fine.
Okay.
It's not problem for you, right?
No, it's not a problem. The meeting will still stay on. I'll just stop the recording right now. Okay. The meeting will still stay on. Yeah. Okay. Yeah. So yes, sorry, I can't stay for longer, Satinder. Is that fine?
So good night, sir.
Good night. Oh, okay. Good night. Thank you. Okay.